Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 22nd lecture of the SwayamPrabha course titled Marine Renewable Energy Systems. In this specific course, which is useful for researchers, capital investors, industrial partners, and of course graduate students and faculty, we are discussing analysis, design and development of new systems for renewable energy. Essentially, in the first phase, we are focusing on the systems related to wave energy devices. Then we will also discuss about the system design for offshore wind farms. Then one more system related to gyroscopic wave energy converter, which is used on ships and mobile offshore platforms like FDSUs, etc. So friends, in this lecture number 22, we are going to take you down to the experimental studies conducted on an example model of a floating wave energy converter. So this study was conducted in IIT Madras. So the credits are to Dr. Srinivasan, who actually performed his research on this design and development. under my guidance at IIT Madras, who was a doctoral student then. Also thanks to Department of Ocean Engineering, IIT Madras, and also thanks to the PMRF fellowship given by Government of India, which supported this study. And now the results of this and some methods used in arriving at this example model is discussed for the benefit of learners in the SwayamPrabha platform. So friends, the contents and the design developed under this are design patented, as you see here, 326436, further design patented, which is 326439 on the same date. So one is for the device design, other is for the hydraulic PTO design, and there's a design patent again 326437, which is on the system of hydraulic PTO design novelty and the shape of the bean shaped wave energy converters. So now these patents are ready for technology transfer, and at wave energy or energy cluster, research cluster at IIT Gandhinagar, we are extending this application to the industrial partners and see how practical and feasible wave energy converters and renewable energy devices can be installed along the Gujarat coastline for the benefit of not only for the state, also for the center power stake. So friends, every novel design always include numerical, analytical and experimental investigations. So nevertheless, this model what we discussed is also conducting or including numerical studies, where we have used ANSYS Aqua platform and also Vexim open source software for developing the novel design of the wave energy converter. We have also solved the equation of motion derived based on the Cummins equation for the novel wave energy converter with different float geometry, with float shape and size, with different sea states, and like regular, weakly nonlinear and fully nonlinear. We have also done this for different wave directions. We have also done this for different PTOs. One example PTO used in this design is an hydraulic PTO, which you can see from the patent document as shown you in the last screen. And then now, to verify and to obtain certain specific characteristics of the design systems, we are discussing the experimental studies carried out on the scaled model of the device. So friends, to conduct experiments, you need actually hassle-free system where waves can be generated. So the primary requirement is the wave climate. So you need wave with a certain amplitude and certain set of periods, wave periods with different directions of heading. So this was possible with a multi-element paddle piston type wheel maker. At IIT Madras, thanks to the administration and thanks to the convenience extended by the Department of Ocean Engineering at IIT Madras. I am still a professor at IIT Madras and also heading the department in maritime engineering at IIT Gandhinagar. So it's a big wave maker or a wave basin of 30 meter with 30 meter size with 3 meter water depth, where we can produce directional waves as well as oblique waves. So now the picture which is shown on the screen is the installed device with 4 bean shaped floats connected to the central buoy. And the top figure shows you the elevation where there is a bridge on the top where the data acquisition systems are placed for inspection. This is a suspended platform where one can inspect the device on motion, and the depth of water at which the study was carried out was 3 meters. So there is a paddle type wave maker on one side creating or generating the waves. The other side you have got the wave absorber. So for convenience and accuracy, there are various electronic devices placed at different locations as you see on the screen, which I will now explain. So now there are 4 wave gauges placed. There are total 4 wave gauges. Which are placed in front of F3, which is this float. Okay. Wave gauge is placed to measure the wave elevation at certain distances from the pedal and between them to find the accuracy of what is the amplitude of the wave exactly approaching the model. Furthermore, at the back of F1 float, we still also have one very close to find out the radiated effect of the waves. So we have 4 wave gauges placed in front and rear of the floats. We have used wire based uniaxial accelerometers and biaxial inclinometers to measure the responses. So the central buoy as well as the floats are being measured for their responses, and all sensors are connected to the data acquisition system, which is located on the carriage at the top as I showed you. So MATLAB interface is being used to access the hardware logged data the experimental model is deployed at the center of the wave basin. center of the wave basin, as I showed you in the figure. Dead weights are placed on the base frame at the bottom, which is being used to anchor the mooring lines. For position restraining the device, so the figure you can once again see this is how it is being installed. So this is the wave basin. At the center, practically the device is installed, the direction where the wave is being activated. And as we discussed in the analytical results also, F1 is placed far away from the wave and F3 is facing the wave first, whereas F2 and F4 are normal to the wave propagation direction. So accelerometers and inclinometers are placed on all the floats to measure the relative displacement between the floats and with the central buoy. So the central buoy and all the floats have accelerometers and inclinometers to measure the pitch as well as the heave motion of this. So now the float, the central buoy is connected to the float by using a hinged joint. So the ball joint is being used to connect the central buoy and the frame to which the floating buoy is attached at the other end. Okay. Now, as the floats are symmetrically placed with respect to the central buoy, the device does not invoke yaw motion. So yaw response is practically zero or minimum to this. The structural damping is not measured in this case because no PTO is attached. The device. So the device is now working purely as a floating platform where the response is measured based on which the PTO will be designed, as I said. Okay. So the scale of the model tested is 1:10. Each float has got 2 ball joints. For example, let's say if you draw a float, a bean shaped float, and I am connecting this to a rafter and there is a interconnecting stiffener arm between the rafter, and here we have got the hinged connections which will make the float to oscillate, and that oscillation or the pitch motion is transferred to the central buoy. Central buoy is somewhere located here. Okay. Now the central buoy is anchored to the floor using mooring lines. The floats are connected to the central buoy using the frame arrangement shown in the previous slide. So now we have got 4 bean shaped buoys connected, one on each side of the central buoy. That's the arrangement we have. 1, 2, 3, 4. This is the wave direction. This is the beach or beach side. Now, nylon pulleys are used to connect the mooring lines to the counterweight at the sea floor. Now the question is, why these pulleys are used? Now they are helpful to adjust the tension in the mooring line. Now the question comes, why do you need to adjust the tension or the force in the mooring line? This is required if you want to adjust the draft of the central buoy. Now the question comes, why do you want to adjust the draft of central buoy? The draft need to be set according to the wave elevation. So if you are running a series of experiments of different matrix of experiments of wave height and periods, you need not conduct the test at the same draft. It won't work. Friends, please understand. Let us try to draw the elevation of this figure again. So if I have a central buoy, if I anchor this, the mooring line to the seabed, and if I am going to provide the float with the frame attached, the float with the frame attached to the central buoy, the floats need to have a draft, and this draft will be related to the draft of the central buoy. So, for a larger wave elevation, the floats should not sink. So, you have to adjust the draft of the central buoy in such a manner that the draft of the float is approximately 40% of the diameter. We have tested till 50%. Okay. To adjust this, you need to adjust the draft of the buoy. The draft of the buoy can be adjusted by providing a pulley and taking it up, and now pull this, you can adjust this tension and you can adjust the draft. Furthermore, you can also add ballasting to the central buoy to adjust the draft. Only the mooring tension alone will not be able to suffice the purpose. Okay. So, there are about 8 mooring lines, 2 for each side, and the axial pull permissible is about 5 kilonewton. That is the characteristic of the mooring line. So, this arrangement we call as turnbuckle system. Okay, this arrangement is called turnbuckle system. Now, as per the design, the central buoy has a buoyancy of about 1600 kg. The draft of the central buoy is 2 meters, and dry ballast which is used to maintain this draft is about 600 kg. Each mooring line is approximately receiving about 500 Newton. Okay, about 500 Newton, which is distributed equally. So, the base frame where the mooring lines are connected or anchored to the sea floor by 1. Excessive counterweights and by the pin and hook arrangement to hold the cables. Now, the sensors are placed on the buoy and the floats. And then they are connected to the data acquisition system to receive the signals. So, one can see the installed buoy in this figure. This is the installed device where the central buoy is in blue color and the floats are in yellow color. You could see 4 floats, F1, F2, F3 and F4. 4 floats, 1, 2, 3, 4, bean shape, and one can see very well the connection of the rigid arm which holds the buoy and the floats like this. And one can also see the counterweight and the arrangement of the moon sickle bearing how these mooring lines are being anchored to the seabed in this figure. The data acquisition system is placed on the frame at the top here, and one can see from this inspection platform the device on motion. Okay, I'll show you a video later at the end of this particular lecture to understand this. Now, let us come to the discussions of the results. So, the setup is being activated now. Let us perform the experiments virtually. Let us look at the results. So, the requirements are, the objectives are to obtain the hydrodynamic coefficients, response time history, and average power absorption, and we need to also estimate the capture width ratio. This is what we wanted from this experiment. Now, we all know that the hydrodynamic coefficients are frequency dependent. What are the parameters? Excitation force, radiation damping, and added mass, which are all estimated using ANSYS Aqua in frequency domain model. Friends, it is very important to understand that experiments in the specific example are not conducted for validation or verification of the numerical studies. They are all complementing each other. They don't verify each other. Okay. So, there are certain things which are frequency dependent, which cannot be estimated from experiments. They are done from ANSYS Aqua. So, those data are taken and used in designing the PTO for the experiment setup. Furthermore, the transfer function of the system of the floating wave energy converter, which is actually the free floating response amplitude, which we otherwise called as operator rho, is obtained in heave motion. Let us look at the figure. How does it look like? So, now let us have the position of G change in the system. Let us say we want to find the influence of position of geometric center G on the FWEC performance. Then only the design can be optimized. Okay. So by conducting these experiments at different G, by altering the ballast positions and the draft of the central buoy, we have understood that the change in G does not influence the hydrodynamic coefficients. Therefore, a position of geometric center is chosen for the floats plus buoy arrangement and kept not varied throughout the experiments. Okay. So the experiment is conducted for different periods and different amplitudes of waves, and the results are plotted. So let us see the figure shown on the screen, which is published in Ocean Engineering Journal paper of ours. So the figure shows 4 coefficients which are drawn for G0 configuration. That is the first configuration of the geometric center. One is the excitation force, the added mass coefficient, the response amplitude operator in heave degree, and the radiation damping. So what you can notice from this is that the device or the floats, let's say F1, F2, F3, F4 are different float configurations or different float positions with respect to the central buoy. You will notice that all the 4 floats are active for a wide range of frequency. Okay, for a wide range of frequency, all the floats are active. It means the device is able to balance its motion for a wide range of periods for which it is being tested. So the test matrix is developed in such a manner that this window can be captured for this frequency and for the adopted scale of the model. Remember friends, F3 is the one which is very close to the wave, and F1 is the one which is away from the wave entry. You will notice that F3 is receiving a good response, as well as F2 which is normal to the wave direction. So this is very interesting friends. So the buoy acts as insensitive to the wave approach angle because the sway is also activated. Remember F2 and F4 are perpendicular, okay, to the wave direction. If you look at the damping ratio measured on a specific float for a specific configuration, you will notice that on a specific bandwidth of frequency, the damping ratio is maximum. So the device will be very effective for this band of frequency for a chosen configuration. However, the device shows damping for a broad range of frequency. Okay? It shows minimum damping for a wider range. For a broad range of frequency, damping is effective. Damping is required to harness energy, friends. The added mass effects can also be seen as a function of frequency, as you see in the screen. and all the 4 floats are active in heave degree of freedom. F3 which is facing the wave showing the maximum heave response. Okay. F1 which is away is showing the minimum response. So friends, the study is conducted to understand the multi-body interaction or to capture the multi-body interaction. So one can see that the device is active in wide range of frequency. It shows active peaks in all floats, isn't it? For a broad band of frequency. So this was conducted by trial and error, friends. In one shot you won't get it. Because the configuration, the number of floats, the diameter, the external peripheral diameter, the central buoy design ought to be done by iterations so that one can achieve this specific aspect of the design. One can also see the PTO damping coefficient. Influences the response characteristics. And this is a function of wave amplitude, wave period, and wave direction. Okay, so frequency dependent parameter, friends. The study is also conducted for different wave approach angles and different wave amplitudes to find the effect of amplitude and approach angles on the damping PTO. Now, when the PTO damping is obtained for different wave amplitudes, for different wave periods, and for different wave approach angles, then one can work out something called the optimum PTO damping coefficient. So this was obtained and we call that as optimum damping coefficient for power absorption. Okay. So from the results, one can say that F1 float, which is placed away from the wave entry, shows the maximum absorption. And that happens as large period. Okay. So therefore, longer waves initiate more power absorption for the provided device compared to shorter waves or shorter period waves. Now the floats F2 and F3 show minimal response. Let us look at the configuration, friends. For your understanding, F1 is here, F2 is here, and F3 is here. Okay. F2 and F3 show minimal responses for short period waves. We call this as interference effect. This is due to the interference influence between the successive floats. As you keep on increasing the wave period, then the power absorption of these grows higher. Friends, there is another constraint we have in this experiment, that the wavelength of the passing wave, we need to compare this with the capture length of the float. If the wavelength is less than the length of the float, in that situation, there will be a crest of the wave at F2 and F4 floats, is it not? Therefore, these floats will not vibrate. We can say will not heave. And this is more or less a resonance tuning for F1 and F3 floats, correct? And this happened approximately at about 1.5 seconds period of the wave in the study. Furthermore, friends, one can also see that the peak of the absorbed power vary with respect to the optimum damping of the PTO. So that says that if the PTO damping vary with wave periods, this will affect the power capture or the power absorption of the device. So the range what we estimated for this experiment is about 1.5 to 1.7 kilonewton seconds meter per radian, and 1.75 to 1.76 for different floats. So now an average of this is considered to compute the capture width ratio of the float. Now let us look at the power absorbed by this floats and compare them to understand their performance in the next lecture. So before I close the summary, I'll also play a video for you. So there is a video which is being played which shows the performance of the device. So in the summary, we learned that the float shape, size, diameter, length and the C states control the design of the wave energy converter. Further, experiments support the numerical studies. They do not supplement, actually they do not verify or validate the numerical studies. They actually are required to support and draw additional information required for the design. That's the beauty of this whole content. So friends, I hope you have followed this lecture and understood the methodology by which this experiment was conducted and how the floats were placed in the wave basin. Credits to the researchers and the institution for providing the support to give this lecture, which will be very helpful in SwayamPrabha domain for people to invent, provide, design and then commission different wave energy devices along the coastal length of Gujarat for its effective size. Thank you very much.